Thanks, everybody. Hi, my name is Adina Feinstein. I am a first-year fellow here at the University of Colorado Boulder, and I'm really excited to have the opportunity to both be a Hubble Fellow this year, or Sagan Fellow, and also talk to you about my science. I also just want to start off by thanking the organizers for making this conference remote-friendly, as unfortunately I wasn't able to be there today in person. So my research program primarily focuses on understanding very young stars and very young planets. And so my PhD work really bounced back and forth between understanding the high energy outbursts from young stars known as stellar flares, while also trying to observe young planetary atmospheres. But over the summer and over the past few months, I have been really focusing in on the flare stuff that I've been working on. So I'm excited to talk to you about that today. So whenever I give these kinds of talks, I always like to start off by highlighting a period radius diagram of the transiting exoplanets that we know of from Kepler, shown in the contours, and then highlighting how the young transiting planets look so different from that. So those are the little blue dots. And so one of the questions that we are actively trying to answer is, how do these young planets evolve? Because we don't see any mature planets with these kinds of radii at the given periods, which must mean that at some point they have to shrink, their radii have to evolve in some way. One mechanism that we often think of is known as photoevaporation, where you have the high energy radiation from your star coming in, exciting your hydrogen helium envelope from the planet and removing that atmosphere over time, and then therefore shrinking, relatively shrinking your radius. And we think that this process of photoevaporation occurs within the first 100 million years or so of the planet's lifetime, when the star is very active and very XUV bright. Now, when we think about atmospheric mass loss, this is really the kind of core equation that we have in mind. So here we have m dot, which is your atmospheric mass loss as it relates to the radius of the planet, the high energy luminosity of your star, the distance from the star to the planet, and then the mass of the core, and also some efficiency parameter eta. But we can't just take this equation as face value, because the high energy luminosity is your star is actually changing on many different times of time scale. So we have to think about. So here we're thinking about like long-term evolution, where you see your XUV luminosity decrease over billions of years, stellar cycles, which can occur on the orders of decades, if not maybe a little bit shorter, and then also stellar flares, which occur on the order of minutes to hours. And so the research that I have been focusing on is understanding how atmospheric mass loss relates to these really short duration, high energy outbursts known as stellar flares. So one of the things that I wanted to think about as a new Sagan Fellow is, how can we use the Hubble archive and all of the far ultraviolet observations that we have of young stars to understand these flare statistics, which we haven't done yet. And so the first thing that I did was I looked at the Ulysses sample, which is a legacy survey of young stars as essential standards. And as I was thinking through these light curves and the data products that they have made available, one of the things I was thinking about is writing an HST archival proposal, which is always a good thing to do, get kind of money flowing. When thinking about writing proposals to understand stellar flares, you really have to think of a strong, compelling figure for attack, because you can never guarantee that there are going to be flares during your observations. And so as part of this mentality, I thought maybe we can extrapolate the far ultraviolet flare rates from TESS flare rates. So TESS is an optical near-infrared broadband observatory that has observed lots of young stars. And so flares tend to peak in the far ultraviolet, so maybe we can do some extrapolation there. So I went into the TESS observations of these stars to try and find their flare rates, measure their flare rates. And it turns out that the TESS light curves had almost no flare rates, which is really surprising for young stars, because we would expect them to be magnetically active. And so this is kind of where I am today, really skeptical as to why we're not seeing any flares from these very young stars. And so this whole process didn't lead to an archival proposal, but it did lead me down a rabbit hole, which is what I want to talk with you about today. And I'm sure many of us can relate to this kind of thought process that I'm describing here. And so the question that I'm trying to answer is, do these really young stars like the Ulysses sample that are less than about 15 million years old really flare less frequently than slightly older stars? So here I'm just going to show kind of a cartoon of the question that I'm trying to answer, where you have the age of the star on the x-axis and the flare rate distribution slope on the y-axis. And so there are three kinds of things that we might expect when studying the flare rate slopes. The first is that young stars flare less, so they would actually have a slightly steeper flare rate slope. They would show no evolution, where you would see this kind of consistent flare rate across all ages. And then also, a third scenario is where these young stars actually have more high energy flares, so they actually have a shallower slope. And so this is awesome. So we have the Transiting Exoplanet Survey satellite, which has observed about 98% of the sky so far. This is a slightly outdated image of what TESS has seen, but I just wanted to highlight, that this has really unlocked a huge population of stars that we can now study that we weren't able to do with Kepler and K2. And so thanks to TESS's All-Sky View and Gaia, and those of you who study galactic archaeology and nearby young moving groups and associations, we now have a lot of different samples that we can draw from. So here I'm just highlighting the sample of stars that I have selected to study, which is about 5,700 young stars with ages of less than about 250 million years old. And so now that we have the data and we have the sample, the next thing that we need to do is go in and find our flares. And so for those of you who don't think about flares often, I'll just give you a brief rundown on how we actually detect these flares in test data. And so previous methods have relied on detecting flares as outlier events above some baseline. So here I've given an example of maybe a relatively quiet star, and I've injected 5 flares in this light curve. Now, if we use these kinds of previous methods, and I'll give you some, random threshold that above it would be considered a flare and below it is not. From these 5 injected flares that I have, I've identified 4 of them, but I've missed the 5th one. And it's really important when measuring flare frequency distributions to understand the full spectrum of flare energy. So you really want to be able to capture these low energy flares as well. Now, this is a really well-behaved star. Young stars don't look anything like that. They look something more like this. So here's an example of a 35 million year old star on the top and a 42 million year old star on the bottom. And you can see that there is this extreme photometric variability due to star spots rotating in and out of our line of sight. And if I were to highlight what a flare on these stars look like, here are just two flares that occur. So you can really see that the kinds of methods that we were using before, you might detrend away your flares, you might miss your flares entirely. And so we needed to come up with a new method to actually find them. So we've learned a lot about machine learning so far in this conference, and I'll give the caveat that we think that machine learning can solve all of our problems, but it can really solve some of them. And so one of the problems that we were trying to solve is if we can find flares in young stellar light curves without having to remove that kind of photometric variability. And convolutional neural networks are a great way to do this because you can train them to find characteristic shapes in time series data. So we've seen that this worked really well in the past for exoplanets, which we can describe very well in an analytical model. And the same thing can be done with flares. Flares have a very characteristic shape in time series data with a sharp rise and an exponential decay. And so a few years ago, I developed this machine learning algorithm to find flares in test data without having to remove the photometric variability. And what it does is it basically slides the neural network across an entire light curve and assigns a probability that a data point is or is not part of a flare. And so as this video is playing, you can see that in just the pure photometric variability parts, the light curve is purple, which means it's very low probability that it's part of a flare. And then when a flare enters the center of the box, it lights up literally, and the network finds that it has a very high probability of being a flare. And so this is great because now we have a metric for like a statistic for flares rather than something is or is not. You can say you're 90% confident that this is a flare. And this method is also really fast. It takes about 1 second to run on a light curve. So it's very computationally resourceful. And so from the sample of young stars that I have, about 5,700 young stars, I identified about 40,000 flares. And I just wanted to give kind of an idea of what that sample looks like. So here on the x-axis, I'm showing age, and then on the y-axis is the number of stars colored by the number of flares. So you see, when there are more flares in your sample, or more stars in your sample, you tend to have more flares, which correlates, and you weight that when measuring the flare frequency distributions. And so I can give the rest of the talk showing you a bunch of histograms, but I feel like that's not really useful, good use of my time. And so I just wanted to give you an example of what some of these flare frequency distributions might look like. So here on the x-axis, I'm showing the flare energy in ergs and then the flare rate in units of per day on the y-axis. This is an example of histograms for M to G type stars, all of stars aged 10 to 20 million years old. And basically what you then do is you have your histograms and you want to measure the slope to see how it's changing as a function of both age and effective temperature of the stars. So I wanted to highlight across all of the associations what those flare frequency distribution slopes look like. And I'll give the caveat that these are very preliminary results. But basically what you're showing here is going from the left-hand side, which is a group that's about 4.5 million years old, all the way out to a group that's 250 million years old on the right-hand side, that the flare frequency distribution slope isn't changing by much. For those of you who are used to exoplanet atmospheres, you're used to looking at flat lines, and here's another flat line for you to look at where you're not seeing any kind of evolution over time. We can bin this into age bins to see, in a sample with maybe more flares, you would see some kind of evolution. And so what I'll show here is then bin down into specific ages instead of specific associations. And so the lines here were representing those 3 cases that I was trying to test, where the dark blue are young stars flare less frequently, the light blue is there's no evolution, and then the yellow is that young stars flare more often. And you can see that even binning down into kind of larger age ranges, that there's really no evolution going on, which shows us that they're statistically not changing over time. Maybe there's an exception where you see an increased flare rate in the M and K type stars at about 15 million years old after the disk dissipates, but I'll have to dig into this a little bit more to see if that's maybe true. And so this still leaves the open question of why these young stellar flare rates are consistent with those in the literature of mature stars, but the Ulysses sample is different. And so as I wrap up, I'll kind of go through the thoughts that I'm thinking now, where maybe the Ulysses sample is biased in some mass space for these stars, but they have a lot of OB stars which are known to flare frequently in the far ultraviolet, which would then probably transfer into the test bandpass. And then they also have observed a lot of K and M dwarfs which are super flary across a range of ages. So I don't think it's biased in terms of sample selection. And then one thing that I've been thinking about is maybe the Ulysses stars are too young to emit observable flares. And so you can imagine a scenario where the accretion luminosity for these stars as they're continuing to form and evolve is actually so bright that it's washing out any kinds of flares that we might be able to detect. And so with that, I will thank you for listening and happy to take any questions.
Thanks for the great talk, Adina. Questions? Okay.
Hi, Adina, Ward Howard. Great talk. I'm so excited that I think your report is the very first time that we've had flare rates for stars younger than, or clusters younger than about 40 megayear. I don't think that exists until now, so this is amazing. I was curious how the change, not just in the slopes, would be across clusters, and you showed that that's pretty constant. But what about for the beta or the Y offset or the R30.5 or something like that? How does the offset change across clusters at a given age?
Yeah, I found that the beta parameter offset is also fairly consistent. I actually have a notebook running in the background right now that has all of those fits in them. So if you want, I can send you a plot after. But yes, those are also very consistent across both age and effective temperature.
Thank you.
Do we have another question? Yeah.
Hi, great talk. This is John Sings. I had a quick question about the reliability of your pipeline. So as someone who saw a lot of my K2, we have tons and tons of really big spikes in the photometry. How do you know that, or how do you measure, or can you measure the reliability of finding these flares and not just say that they might be from your spike in the instrument?
Yeah, so the way that we train the pipeline is actually on a catalog of flares that were hand identified by eye. And so in that sense, we were able to rule out a lot of kind of systematics that you might see like at the beginning of a test orbit or any kind of these random like 1-point outlier spikes. One of the things that I have noticed, and I'll give the caveat that the pipeline isn't perfect, is as TESS has continued to observe, the systematics have changed sector to sector. The pipeline that we have was trained on data that was observed only in sectors 1 and 2. So there are some kinds of additional cuts that we have to do behind the scenes to remove those potential systematics. I didn't highlight that here, but we can talk more about that if that's something of interest to you. But yeah, it's not perfect. It does a good job, but yeah, there are some caveats there.
Okay, thank you very much. Everyone put their hands together again for Adina. Okay, and now for our next talk, we've heard about some of the younger stars, and now let's hear about some of the older stars. So for our next talk, we have Tim Cunningham, who's a Hubble Fellow at Harvard, in a very long distance to tell us all about white dwarfs, probes of convective overshoot, and evolved planetary systems. Take it away.
Thank you very much. Can you hear me? Yeah? Okay, great. Yeah, good afternoon, everyone. Thanks. Is it okay? Is it loud enough?
I don't think it's being shared.
Oh, right. Yeah, we should do that. Okay, how's that? Hopefully people online can see. Yeah, good afternoon. Thanks for having me. Thanks to the organizers for a great conference so far, and thank you to NHFP for providing me the opportunity to start as a Hubble Fellow this year at CFA. Yeah, I haven't traveled far this morning, but I did come from England just a week ago, so I'm going to count that as a long travel. Yeah, today I'm going to tell you about lots of things I've been working on over the last few years and my visions for some of the things I'm going to work on for the 3 years of this fellowship. The title says, yeah, white dwarfs as probes of convective overshoot and evolved planetary systems. I'm going to try and tell you why white dwarfs are vital for many things, from atmospheric physics to our understanding of exoplanetary material. I'm going to kick off, okay, with collaborators that have helped me along with many of these projects. This is a cobbled together quick overview of what we know about the stars that show signs of exoplanets or exoplanetary material. I took all the known exoplanet hosts from the NASA Exoplanet Archive, which you're seeing there on the main sequence, and the giant stars. But I want to draw your attention to this sequence here. These are white dwarfs that have metal pollution. There's around 2,000 of them now. Most of them we think are actively accreting, and they provide an amazing opportunity to study the compositions of the exoplanetary material that was accreted onto them. It's comparable to throwing our planet into a mass spectrometer, and it's the only way that we can really measure the bulk composition of exoplanetary material. So why do white dwarfs work for this? White dwarfs, as we all know, are about the mass of the sun and the size of the Earth. This high surface gravity leads to gravitational sedimentation on very short timescales. So within a few tens of millions of years after the white dwarf formation, it should reach a stratified structure such as this, with a carbon-oxygen core, then either a pure hydrogen or helium shell. That was true until 1917, when Van Manen 2 was discovered to have metal lines. Although at the time it was thought this was probably an F or K star. But looking back, this was really the first evidence of exoplanetary material in the galaxy. You're seeing here a helium-dominated white dwarf with calcium, H and K, magnesium and iron lines. Since then, this is the progression of the discovery of metals in the atmosphere of white dwarfs. And I'll draw your attention to rock-forming elements, as well as elements that are necessary for life. And yeah, I quite like the perspective of this plot, because I'm very interested to know what we're going to find in the years to come. So we now, thanks to Gaia, have 360,000 white dwarf candidates. About 30 or 40,000 of those have been spectroscopically confirmed. And that number is rapidly rising with the dawn of MOS surveys like DESI, WEAVE, Foremost, and SDSS5. When we look at HST samples and spectroscopic samples, we tend to find about a quarter to a half of white dwarfs show signs of metal pollution. So there's lots of white dwarfs out there, which we can do a lot of exciting science with. How does this metal pollution arrive at the surface of a white dwarf? We think that at the end of stellar evolution, the planetary bodies that were orbiting the host star will be, the orbits will be disrupted, and this will trigger gravitational instabilities, which will throw planetary bodies, whether it's moons, asteroids, or planets themselves, to within the Roche radius of the white dwarf. The Roche radius is about the solar radius. It's about 100 times the size of the white dwarf. So there's a large catchment area for catching planetary bodies. And we have lots of evidence of this being the case from infrared excess. That was the first hint that we have circumstellar dust. We also have gaseous emission lines. So you're seeing here in the top right, calcium, with calcium triplet with Doppler splitting due to the Keplerian orbit. And we also have transits of planetary bodies. So there's now at least 10 systems that actually have transiting debris. And we also have planets around white dwarfs as well. But the key evidence for metal pollution and of all planetary systems is the presence of absorption lines in the atmosphere of the white dwarf. These are just typical occurrence rates based on observations so far. Now, all of the thousands of metal polluted white dwarfs that we have now, which are metal polluted, provide indirect evidence of ongoing accretion. Because the sinking time is so short in white dwarfs, we think if the metals are there, then they must be constantly replenished. That's true in most cases. But this is indirect evidence of accretion. I will present at the end the first direct evidence of ongoing accretion, which we achieved using the Chandra X-ray Observatory. That's all celebrating. So so the typical way that this works is that you take an optical or UV spectrum of your white dwarf and you see metal absorption lines in the otherwise pristine helium or hydrogen atmosphere. And from that, you can derive a metal abundance. Couple that with a white dwarf atmospheric model, you can get a sinking time. From that, you can derive an accretion rate. And really, that's the tool that can be used for probing these evolved planetary systems. So we can learn about the amount of mass that's been accreted. We can learn the relative amounts of mass between different elements, and from there, make some inferences about the composition of the parent body. But in order to do so, we really need to know the white dwarf atmospheric physics very well. One of the key uncertainties is the treatment of convection. This is a toy model. White dwarfs develop a very superficial surface convection zone as they cool. It probably never gets geometrically this big. It really starts at like 10 to the minus 17 of the mass contained in a convection zone, but this grows as it evolves. There's a big discrepancy that's been present in 1D modeling of convection in all instances, in that if you model convection using mixing length theory, you have convective velocities, say kilometers per second, and diffusion timescale is much, much shorter than that. So I spent quite a lot of time studying the convective overshoot, which is a physical phenomenon that arises to effectively extend the size of the convection zone. I do this using the 3D hydrodynamics code COBOL. This is just to show you that we get granular convection at the surface of white dwarfs. On the right is a simulation. On the left is an observation of the sun. So it's just to show you qualitatively that we recover this granular convection. This is some slices from my simulations. I don't have much time to kind of go into this, but I'm happy to discuss this in more detail. But the takeaway here is that we have lots of mixing outside of the traditional convection zone. And this leads to various things, including a predicted higher accretion rate. I'm going to skip forward a bit. So we tested this, we wanted an independent test of the accretion rate of these systems in order to test these overshoot models. So we turned to X-ray observations. Chandra was the only instrument capable of observing this particular system due to its angular resolution. The X-ray observations gives us a very nice independent constraint on the accretion rate because we don't need to know anything about the white dwarf atmosphere, only its mass and radius, and then much easier to constrain. So last year we had the first detection of X-rays from a metal polluted white dwarf. So this is the first direct evidence that these things are undergoing active accretion, compared to, say, the black holes that we heard about earlier, which might have X-ray luminosities of 10 to the 40. We measured an X-ray luminosity here of 10 to the 25. This is our source in the middle here. This bright contaminant is the reason that XMM is not suitable for this observation, but I think it would be for many others, and that's something I'm very interested in pursuing. So we measured the spectrum of this system. We had 5 counts, which is not very many, but they still tell us a lot because Chandra's ACIS gives us spectral information. So here I'm showing the sensitivity of Chandra's ACIS instrument at the top. All of our counts here in black were very soft. And this tells us quite a lot. It tells us we have a very soft spectrum because our counts arrived in the region where ACIS was least sensitive. So one thing I have as an ongoing campaign is to try and improve our constraints on the extreme ultraviolet flux using joint Chandra HST observations. So we measured the accretion rate from these X-ray observations, and that's what I'm showing here in blue, various assumptions about the composition of the infalling material. The green and the pink are models that have overshoot and not. This was published earlier last year. One of the key uncertainties in this is an upper limit on the accretion rate. So here we have highly asymmetric error bars. This is because we can't unsee photons, but we don't know how much flux is being carried in the extreme ultraviolet. That's one of the main things I'm interested in improving. I've recently had a 4-cycle multi-cycle proposal accepted with Chandra using the HRC detector, which will give us much higher count rate because it's more sensitive in the soft. We don't get spectral information, but it's going to allow us to probe variability over yearly timescales. And the diffusion timescale of this object is about a year, so we should be very sensitive to variability. So we've got the first detection of X-rays, and now we've got the first opportunity to probe variability in the accretion rate. And I should say that this system is variable in the infrared. So we know that there's some activity in the disk, and we want to know, is there any causal connection between the disk variability and the accretion rate? So I'm just going to leave some future ideas I have and things I want to work on during this fellowship. As I mentioned, I have a Chandra HST collaboration. This object in particular has had 35 HST orbits. And so we can do a joint modeling of the two to improve our constraints on the EUV. As I mentioned, we have this program with Chandra to look at variability. I'm also developing an analytic model of convective overshoot to tackle cooler white dwarfs, which I didn't have time to get into here. But if you're interested in any of this, I'll be very happy to take your questions and talk to you offline. So thanks for listening. And yeah, thanks.
So questions from the audience.
Nice work, Tim.
Yes.
Can you talk a bit about how many of these objects you expect to see in the future?
In the X-ray or just in general? Yes. Yeah. So this is the object we've detected with Chandra. So these are all metal polluted white dwarfs with hydrogen atmospheres, which account for about 80% of the sample. So these are all metal polluted white dwarfs. I would say anything above about, so yeah, as the white dwarf cools, the convection zone gets deeper, the diffusion timescale gets longer. So it becomes less of a safe assumption that it's actively accreting. But yeah, so this is the sample, but I'd say the very cool ones, we can't be confident it's actively accreting because the diffusion timescale gets to almost 1 million years there. But for anything above kind of, I don't know, 7,000 Kelvin or so, I would think it's fairly safe to assume it's actively accreting. So I'm showing here the kind of detection limits, assuming about 100 kilosecond observation with Chandra XMM and a proposed X-ray mission axis. So yeah, this is a vision for the future.
Thanks.
Okay, another question. We need a question this side of the room. Is anyone thinking over here? Okay, fine.
The last question made me wonder about EOZ. Maybe it's a little too shallow, but there is a data release coming.
I know, yeah.
But I was just sort of wondering about a little background, since I don't know much about this topic, on how the planets get so close and how the debris disforms. Does that fall into sort of common envelope processes during the red giant branch, or what?
No, I don't think it really requires any common envelope explanation at all, but simply that your host star loses maybe 50% of its mass. So all the orbits expanding, and then that will trigger many gravitational instabilities. So if you just allow that system to evolve for long enough, you'll end up flinging asteroids and moons and planets themselves. There's been lots of N-body simulations and theoretical work to back that up. And so I think we've got good theoretical understanding of how you might trigger these instabilities. It's much more difficult to work back from a particular system and say, okay, this must have been a Jupiter mass planet with an asteroid. But yeah, we can certainly show that it can happen.
Thank you very much, Tim.
Sure. Thank you.
Okay, so we've heard about dead stars. Who's up here about dead planets next? Oh, I see some excited Galaxy and Collider people in the audience as well. Okay, so Joel, why don't you tell us about astroseismic signatures of planetary engulfment?
Hello, Hakako. Can everyone hear me?
Can we check that's on?
Yes.
Yeah. That should be on.
Thanks for the opportunity to speak in person. I want to talk to you today about a work that has been the fruit of some collaboration with other Hubble Fellows listed on my title slide, to whom I must also give credit. Okay, so for the benefit of those who are not familiar with the general phenomenology of solar-like oscillators, I will first give a brief overview. So solar-like oscillations are pulsations in stars, which are the pulsations and not the stars are like those we see in the sun, right? So for the sun in particular, we're able to take, images or alternatively radial velocities. And if we were to integrate the radial velocity or the brightness of the star over the disk, we would be able to obtain a time series of the kind that I've shown here. That's very much stuff to deal with, and we don't want to deal with all this at once. So we instead work in the frequency domain, where typically we would see for a solar-like oscillator a series of peaks like that shown. Each series of peaks. So you can see that, we have several series of peaks, each of which is separated by a characteristic spacing delta nu, right? And I put the solar values here for the sun. We also have a characteristic resonance frequency called nu max that is about 5 minutes. And delta nu and nu max together depend on the global properties of the star, such as its mass, radius, and effective temperature. Because of the regularity of the peaks that we see, the frequency domain, it pays to rearrange this data into a form that makes it easier to reason about. So what seismologists typically do is break the power spectrum down into chunks of equal with delta nu. We stack the chunks in increasing order of frequency like shown to form some kind of three-dimensional structure, which has the morphology of distinct ridges of modes, right? So each ridge is made of many modes. Each mode is a normal mode of oscillation. Now, I want to zoom in a little bit on these ridges because they actually have some substructure that is not immediately obvious. So you can see that this ridge is made of single peaks. This ridge is made of triplets. This ridge is made of double peaks, and this ridge is made of quadruplets. So the idea is that each of these ridges corresponds to a spherical harmonic L, which gives you a different multiplicity of modes. Right? And the other defining property of solar-like oscillations is that they are stochastically and broadband excited. So within the range of frequencies set by the resonance frequency, basically every mode that can have kinetic energy will have kinetic energy. And so the mode amplitudes are roughly consistent between components of each multiplet like this. So these multiplets arise because basically every star rotates, right? And the pulsations interact with the rotation in a fairly well understood fashion. So like I said earlier, different ridges correspond to different spherical harmonics, and the spherical harmonics tell you basically the horizontal shapes of the eigenfunctions of pulsations, right? And different spherical harmonics are indexed by the angular degree L, which in turn give you different amounts of degeneracy indexed by the azimuthal order M. Right, so in the presence of stellar rotation, there are modes which propagate around some notional rotational axis, whose oscillation frequencies will appear to increase in the presence of rotation, and the modes which propagate in a retrograde sense will appear to oscillate more slowly. And so this causes what would be a degenerate single mode frequency associated with a degree L to split into a multiplet of peaks. The inclination axis of the stellar rotational axis, the inclination angle of the stellar rotational axis relative to a stationary observer will also determine which modes will appear to oscillate the most or cancel out when integrated over the visible disk. So the result of this observationally is that in the presence of rotation, a single mode in the power spectrum is split into multiplets, right? With the multiplicity of the multiplet determined by the angular degree L, and with the inclination angle of the rotational axis relative to the observer, determining the distribution of power between modes in the multiplets. So in particular, if we are seeing the star equator on, then each multiplet will have L+1 modes for angular degree L. The other card I want to lay on the table is that we can also use the modes of oscillation themselves to determine the properties of the star. If we only have access to the global parameters delta nu and nu max, we can constrain evolutionary models to obtain stellar masses, radii, and ages, of which I showed posterior distributions here for a modeling exercise that we did a couple of years ago. If we have the mode frequencies themselves and are able to constrain evolutionary models using them as well, we can considerably tighten our estimates of these stellar properties. So I've now put some cards on the table, and I want to talk to you in particular about a rapidly rotating red giant that we've seen in tests. The light curve, the test light curve for the red giant seems fairly innocuous, but the reason why we looked at the star at all is because it has a very high lithium enrichment, right? So to remind you, the power spectrum for the Eshell diagram for the sun looks like this. You have vertical ridges, each ridge corresponding to a different angular degree L. Right. In particular for the sun, the L=0 ridge lives here, shown in blue, and the L=2 ridge lives here, shown in gray. So if you look at the Eshell diagram for this red giant, you also see a double ridge feature, and it is therefore tempting to identify this ridge as being the L=0 ridge, and this ridge as being the L=2 ridge. The problem is that such an identification is inconsistent with every red giant we've seen with Kepler. So if you look at the Kepler sample, all the L=0 modes live here on the Eshell diagram, right? Which means that we cannot identify this double ridge as being comprised of L=0 and 2 modes. So the only consistent identification we were able to arrive at requires us to assign to these double ridges an interpretation of being a set of dipole modes seen equator on. Having assigned such an interpretation to this double ridge feature, we have also to place our radial modes here, where the Kepler sample requires them to live. Together, these form a consistent mode identification of a star that is rotating relatively quickly at its surface and is also viewed equator on. With such a mode identification, we are then able to prosecute our usual statistical procedure for astroseismology, which I imagine is not of significant interest to this audience in particular, but I will focus on a subset of the posterior distribution, which I showed in this corner plot. What I have derived here is a posterior distribution for the inclination angle of the star, which, as suggested by our mode identification, is seen equator on, as well as independent estimates for the surface rotation rate as derived from L=0 and L=2 modes. Together, they imply a surface rotational period of about roughly 100 days. However, this is kind of absurd. If you were to place a star, on zero-age mean sequence at maybe the breakup rotational speed, shown with the black curve, and let it break magnetically, by the time it reaches this point on the red giant branch, it would be rotating at a rotational period of several thousand days. And there is basically no physical explanation for how we would arrive at a rotational period of 100 days under the standard picture of single star evolution. The other problem with this is that if you look at the light curve, you don't see 100-day modulation associated with rotation, at least I don't. And it is therefore likely that such a rotational signal probably got detrended away by the standard systematic error corrections that are applied to this publicly available test data product. So we did our own systematic error correction, and a 100-day modulation does indeed pop out. But we can't say for sure, just by looking at this, whether this is genuine or induced by our custom error correction and willfully conjured into existence. So to verify that such a modulation is indeed real, we also got photometry from the Assassin network of telescopes, and you can see that the Assassin signal, which is from the ground and therefore independent of test systematics, does also give you a 100-day modulation, and so we are pretty certain that this 100-day period is real. So to finish laying the cards on the table, we have estimates of mass and radius from the star from seismology as well as rotation. We have an independent photometric rotational estimate that is consistent with seismology. And we also have spectroscopy that gives us a V sin I that is consistent with our seismic rotation period, as well as a relatively high lithium enrichment for the star. Finally, we have radial velocity scatter from Gaia DR3. And together, these constrain the possible formation hypotheses for such a system. So let's, for the sake of argument, suppose that such a high rotation rate was produced by tidal locking with a hitherto unseen planetary companion. I show on this diagram the possible parameter space of potential companion orbital radii and companion masses. The Gaia RV scatter rules out radial velocity sampling amplitudes that are too large, right? And so given our measurement of the Gaia RV scatter, we can rule out all possible companions in this red part of the parameter space as possible explanations for this rotational configuration. Also, a planet in, let's say, a 200-day orbit can't spin a star up to a 100-day rotational period, right? And so in order to potentially explain such a rotational configuration, any potential planet cannot live in this orange part of the parameter space as well. And this leaves only the small window of parameter space available as potential explanations for how this star came to be. It turns out, however, that planets in this part of the parameter space are also unstable to tidal dissipation. So the conclusion that we draw from this exercise is that we have no choice but to consider the possibility of such a configuration emerging from a planetary engulfment scenario. Conversely, if we assume a priori that such a configuration was produced from an engulfment and attempted to solve for the companion mass and orbital separation that is consistent with the observed amount of angular momentum in the system, it turns out that the primary source of uncertainty in such an estimate is the viscous damping timescales shown as TV1 in this figure. But if we were to effectively marginalize over 4 orders of magnitude of possible values of TV1, it turns out that the estimates of a companion mass and its initial orbital separation don't actually change all that much. And so we are left with the conclusion that we have a rapidly rotating red giant that cannot have been produced by single star evolution. It's also abnormally lithium rich, indicating that some other weirdness has gone on mechanical mixing, and whose dynamics indicate that it cannot have been produced by anything other than some kind of engulfment scenario. If we take an engulfment scenario for granted, it must have happened within 5 million years, within the last 5 million years. You can ask me more about how we came at that conclusion. And it must have had a companion mass initially of between 6 to 10 Jupiter masses. Thank you for your attention.
Any questions for John? Yeah. Thank you, Joel, for an awesome talk. How did you come to the conclusion of 5 million years?
Okay, so all right. So I've discussed earlier that if you place a star on the main sequence and let it magnetically break, it breaks to a rotation period of thousands of days on the red giant branch, right? But we can do the converse. We can say I have a star that's a red giant rotating 100 days, and I run the breaking calculations in reverse. And if we do that, we find that it will have reached, it will have to have had been rotating at breakup speed about a couple million years ago in order to break to a rotation period of 100 days today. And so if the engulfment happened before that, then it would not have resulted in a hydrostatically stable configuration that would also break to the red giant that we see today. So this places an upper bound on how long ago such an engulfment could have occurred.
It's always magnetic fields. Okay, we've got time for 2 more questions. Okay, Dick. Thank you for the suggestion, Ryan, for question. Do you take into account okay. This, do you take into account magnetic interaction of it?
No, we don't. So the only inputs into this magnetic braking calculation are Rossby number scaling for the magnetic field of the star, and that's it. There is no planetary magnetic field involved in this calculation.
Well, if there are no more questions for John, we'll move on to our first before lunch. Thank you again very much, John.
Yeah, finder. Here we go. It's already screen sharing, right? So we should be fine.
Yeah, we should be fine on that front.
It does, yeah.
Oh, exciting.
Okay, and continuing apocalyptic theme. And now we're going to hear from Melinda Soares-Furtado on stellar epitaphs, the final testimony of devoured worlds.
All right, thank you so much. Thanks to the organizers. Thanks for entertaining this silly name. Yeah, so I'm going to start off by just trying to convince you that planetary engulfment is actually not a very rare phenomenon, and it's something that we should be thinking a lot about. So if we combine the known exoplanetary population into a single animation, where I really want to get a sense of like the orbital separation from a typical host star. This is a simulation that was put together, an animation put together in 2021. We could add many more objects to this plot since that time. Doesn't really change the scale all that much. The typical exoplanetary host is actually not very different in terms of the sun when it comes to the mass and when it comes to the evolutionary state. But as we all know from this session, stars evolve and change significantly in their size. And if we were just to take this toy model and expand these typical host stars, what we would find is that the vast majority of the known exoplanetary population, for which we're very biased in terms of finding close orbiting massive bodies, just because of the radial velocity and transit technique, which tends to unveil most of them at this point. These are objects that are actually doomed to be engulfed. And in fact, if we take into account occurrence rates and try to remove these biases, a third of all sun-like stars, what we know the most about when it comes to exoplanetary hosts, have planets larger than the Earth that have orbits shorter than 400 days, likely to be engulfed just due to the size that the star will expand to on the red giant tip. And this does not even account for rocky bodies, which are also very interesting in other ways. But many planets have actually already been engulfed. We have a bias towards detecting planets around main sequence stars that are still actively burning hydrogen in their cores. But we're learning more about planets orbiting slightly evolved stars and even pretty evolved stars. But what do we expect to accompany an engulfment event? What sort of signatures do they leave behind? For those of you that were at the Hubble Symposium last year, you might remember Kisha Day's talk about the transient events that can accompany these events. Very interesting that you can actually see in in the time domain, these sort of markers. There's also the possibility that you can eject the outer stellar envelope, perhaps leaving behind infrared excess. And so I'm just going to point to some work that has been done with a graduate student that actually led to a little bit of a splash. There's the engulfment stuff, I think gets picked up by the news pretty frequently because you get these kinds of headlines, the juicy secrets of stars that eat their planets. But it was actually very interesting work that Ricardo Yarza at UC Santa Cruz will be graduating soon and on the postdoc market, did with the flash hydrodynamical simulations, where he looked at planets, companions at different orbital separations and different companion masses to try to get a sense of what sorts of objects will cause their stars to eject their envelopes. Also, you can take these orbital separations and you can think about this in solar radii space. We're really thinking about a star expanding and at that point of its size, then interacting with its exoplanetary companion. And I want you to think about down here, we have planetary companions, but we're also probing in this parameter space brown dwarf companions. Everything that is sort of inside this hot Jupiter line is really close orbiting companions, but we actually went out all the way to 1 AU. And we found sort of 3 different spaces here. So if we're thinking about a typical star, this is like a sunlight model that's sort of giving you the scale size of the convective zone would be, the radiated zone. We wanted to get a sense of for various companions, how this will change. So the orbital separation of the solar radii is now probing that evolutionary state, that change of internal structure. And what we found was you have to be pretty massive and pretty distant around a pretty large star to eject the envelope. It's actually quite difficult to do. May explain why infrared excess is not so frequently seen. But there are a lot of objects that have been destroyed below the convective regions, or a lot of systems. These are your still more massive, a little bit more distance. And then your closest companions at the lowest masses can be destroyed into that convective region. And that's really interesting for me because I like the spectroscopic component of this, of being able to observe this in the stellar spectra. What sort of enhancements, maybe even beyond lithium, can we observe? For those of you that are interested in talking offline, we have reason to believe that this might even be a little bit easier to disassociate your planet than previously thought. Maybe these cores don't want to stay bound. And once you disassociate a certain amount, it actually lends some help. And so it'll be interesting to recalibrate this with that in mind. So I'm interested in the chemical enrichment signatures. When thinking about what sort of chemical signatures you might expect, I thought about using chondrites as a proxy and comparing the chondritic abundances to solar abundances. The vast majority sort of live on that 1-to-1 scale. It makes sense. They form from the same molecular clouds. You have your noble gases, of course, that just basically need to be around a more massive object in order to remain gravitationally bound. Here's an example of a typical chondritic specimen one might find. So your volatile species and your noble gases, those will you find preferentially in stars because of that mass dependence. But lithium, which is this fragile trace element that's destroyed at 2.5 million degrees Kelvin, never reaches those temperatures in substellar bodies. And so these lower mass objects preserve their initial lithium supply. It's a really useful flag. But a star can also self-enrich with lithium. It's not the only flag that we would like to find. However, just taking lithium as sort of a first step, how statistically significant can lithium signatures be if you were to engulf an entire Jupiter mass worth of material into the convective zone of a star? It's a question that I asked and that I wanted to explore using baseline lithium abundances from GLOS survey data as a way to get a sense of what the typical amount of lithium a star should have and the typical amount of variance that lithium signature in the field would show for stars of various masses and evolutionary states. And what we found was, let's take every single point and post-process in MESA, add in the number of lithium and hydrogen atoms that a star, if eaten at that point on the stellar track, would liberate, and get a sense of how statistically significant that signature would be. So let's do that there, right on the main sequence turnoff for a solar mass star. As we see pretty low statistical significance because there's a lot of mass in that zone, very dilute signature. Let's do it at a later stage where you have more mass in the convective zone. You're seeing the statistical significance going down. So we did this and also taking into account that the variance is changing, which is why it's not strictly monotonic. And what we found is a small range. There's a small location of masses and evolutionary states where lithium is a really useful tracer for planetary engulfment, where maybe you can even back out the amount of mass that was ingested. And so I've been specifically looking at systems at this mass and evolutionary state range and trying to find other flags like maybe orbital architectures that infer some kind of recent dynamical scattering process to now look at signatures beyond lithium. What's also exciting is that the following year in 2022, there was a scene in a Lamosque pileup of data that enriched giants and compared to normal giants tended to be straddled between that 1.4 to 1.6 mass range that we saw as being a preferential location. Not that more engulfment is happening there, but when it's happening there, it's able to be observed in a very statistically significant way. And that's been reflected in surveys following that result. Okay, but what's next? As we know, some planets have already been ingested by their aging stars. Can we find them? This is something I very much want to do. How are the properties of these stars distinct from others that have not ingested planets? This is really helpful if I find them in co-moving groups, widely separated binaries, but we're not always that lucky. And are there other tracers beyond lithium that I can find that don't have degenerate pathways? Stars aren't able to self-enrich in the ways that they can self-enrich with lithium. This would be very useful because maybe I can even learn about the mass of the companion that's been ingested in a more accurate way. And maybe learn about the bulk properties of that planet. And so I've been working with an undergraduate student as part of her honors thesis and during the Lamont REU program, Brooke Cotton, who's at the University of Wisconsin-Madison and applying for grad school this year. She did an amazing job actually analyzing an interesting source shown there by the gold star on a couple different isochrones. This is a pretty early subgiant star that we see that has enriched lithium signatures, and in addition to that has a close orbiting, highly eccentric, massive companion. So something dynamically interesting has likely happened to this object. And what we did was we looked at lots and lots of radio velocity data, co-added it to get high signal to noise, has amazing spectral resolution, in my opinion, 44,000. And she went and found a control sample of stars. This is just two of them that are shown for comparison here, to get a sense of, in addition to lithium being stronger in our target, there's usually squeezed between these two objects that are slightly more iron rich and slightly more iron poor. Where else do we see strong departures of strong absorption features? And in fact, she's identified 30 specific features corresponding to 10 different isotopes. And I'm very excited about the possibility that we can now work with planetary scientists to get a sense of how deeply deposited these species might be. Are they part of the lithophiles, the chalcophiles, the sidereophiles? Can we get a sense of how fully disassociated our planet is? Can we get a sense of how much mass these different elements would give us that must have been ingested to give the sort of signatures that we're measuring? How does that compare to lithium? Because we know lithium is degenerate and is also a tracer of extra mixing. So this is very exciting. We're hoping to put this paper out this fall. We would like in the future, with more time, to curate data to get a larger control sample. We have about 10 stars that are really good controls at the moment. But we are finishing analyzing the statistical signatures, making sure we've identified the lines correctly with experts who've done this for 30 years. And we would love to get estimates individually of the masses of the planet that we think has been engulfed. Lithium infers something like 5 Jupiter masses. What do other species say? By the way, that 5 Jupiter masses is still much less massive than the companion, which is interesting. And yeah, that's where we're going forward. And before I end, I just wanted to mention, because this is an amazing opportunity to continue to collaborate. I've been very happy working with Mark and Joel. There's a couple other projects that I'll just mention. I'm working on an analysis of NGC 6819 and NGC 6791 with Brianna and Nicholas, 2 undergraduates, and graduate student Rachel McClure. Lots of interesting blue straggler variables in that population. We're classifying the different kinds of variability. We've already performed image subtraction on those light curves. I have a new graduate student, Julia Scheffler, who's going to be looking at Ursa Major, this co-moving group we're embedded in, using SALT and using trace data to try to better analyze the age of that system by defining the main sequence turnoff, searching for more planets. We've already found an Earth-sized planet orbiting a sun-like star at 400 million years old, because that's how old Ursa Major is. And Ben Capistrand and Melissa Jankowski have been looking at the analysis of that system, which is around a very bright star, conducive for more follow-up. And I'm really a big proponent of using Roman to do time domain analysis in the infrared, really short integration times around star forming regions like the Orion Nebula cluster. I'm very interested in, if you had 30 days at 18-second cadences of analysis from Roman, 2 microns staring at the ONC, what would you do with it beyond what we're interested in, which is looking for exomoons around free-floating planets? Because a lot of science accompanies this, and maybe this is a good way to sort of get a community together to have a proposal that would be successful. And with that, thank you so much for your time.
Melinda.
Very nice talk, thank you. If I understood correctly, you said that if you have an engulfed planet, it is not as easy to eject the stars outer layers. Can you please elaborate more on why is that the case and what kind of condition? I know you showed the plot, I couldn't probably follow on what conditions you need to eject the stellar envelope.
It's really about angular momentum transfer. So more mass and longer lever arms work in your favor, and more mass being that secondary companion. So brown dwarfs separated at about 1 AU would be very successful at doing this. It gets much harder to do when you get to sort of the typical planetary composition that we're used to thinking about. But whether or not you're destroying in the convective region or in the radiative region or the convective region, I think there remains to be some more work. I hadn't appreciated this idea of overburdened pressure until very recently. But it's quite difficult to actually, and when we're talking about ejecting the envelope, we're talking like half a solar mass being ejected from a sun-like star kind of envelope, substantial amount of material to be liberated. It's quite difficult to do, but it might explain why when you find an engulfment candidate, infrared access is not always seen.
Oh, is that on? Yeah.
It's sometimes on, it seems.
So,
I'll repeat it for the audience if you like.
Yeah, I was just curious, like where pulsations fit into your work, how many of your targets are pulsating, and if there are, does it provide noise, and can you exploit the pulsations so that can
So, Tim Cunningham asked about how pulsations fit into this topic and what we use them for, whether or not they're sort of signal or noise. It's helpful with the red giant like oscillators that have these pulsational modes like Joel was just talking about, because you can infer things about the internal structure. So whether or not angular momentum is fully deposited on the surface is shown in that photometric rotation. So rapid rotation is another really useful signature. You can now start to probe interior structure and get a sense of maybe the object slowly disassociated and depositing angular momentum, sort of in a way that shows some kind of radial profile there. So that's useful. I also work on blue straggler work when I'm thinking about stars merging and sharing masses, and comparing the mass that's infirmed by astroseismology to the mass of the main sequence turnoff can be very useful. But with planets, I haven't yet found a way to be able to do this. Now, whether or not a planet can create a blue straggler is something I'm very interested in. How much mass does it take? What does the accretion rate need to be? How dissimilar can the amount of material accreted be to then create sort of differences in the opacity and the molecular weight and have maybe a transient blue straggler? It's something I'm trying to simulate with MESA. So more to stay tuned. But yeah, the rotation is another really useful indicator. And I really love the idea that with seismology, we can actually probe interior rotation and structure and not just what's sort of seen on the outer parts of the star.
Please put your hands together for all of our stellar speakers in this. Now, if hearing about stars eating planets have made you hungry, I have good news for you. Lunch is served.